Welcome, everybody. Welcome, everybody, for the One Well seminar in cognitive psychology. Today's is the last seminars of the series of this academic year, and it's just a great pleasure for me to welcome a friend, Claudia Von Bastian, from Sheffield University in the UK. Let me just say a little bit of what Claudia did in her life, and actually she worked a terrific topic, which is cognitive individual differences and cognitive ability and training, what she's going to talk about today. Claudia obtained a PhD at the University of Zurich in Switzerland with Klaus Obrauer. Then during that time, she already been a little bit in the UK while she was working at Bristol with Chris Jarrold. And then after a PhD, she moved in the United States to work with Akira Miyake at Boulder and then with Mike Kane. And she loves so much the UK. Then she moved back to the UK where she was lecturer at Bournemouth University before moving to Sheffield, where she's nowadays. So it's my great pleasure to hear you today. She's also very strongly involved in the Psychonomic Society because she is an associate editor at the journal Behavior Research Methods. It's really interesting work she's doing there. And she also organized some specific event with Mike Kane at Psychonomic New Orleans a couple of years ago. So I'm so thrilled to hear to you, Claudia, and welcome. Please, it's your turn.
Thank you so much, Valerie, for this very kind introduction. And it's such a pleasure to be here today and a real honor indeed to speak in this seminar series. So today I want to talk about some work we've been doing on the mechanisms of cognitive training and transfer effects, and specifically two mechanisms, and those are capacity and efficiency. So one of the questions that really propels my research is how do people differ in their cognitive abilities, and why do they do so, and what can we do about that? And this last part of this research question, what can we do about that? I try to address that with cognitive training. That was like one major part of my research so far. And you might have come across some of these kind of cognitive training interventions that try to improve cognitive performance, labeled often as fitness for the brain or brain training and so on. You might have seen some of these or all of these apps and programs that you can do. So for example, Lumosity is like a pretty popular and famous subscription-based app that you can use. And the typical way how they work is that you repetitively practice some cognitive tasks. And the idea is that from repetitively practicing them, you're not only getting better at the specific task, but that you practice some underlying cognitive processes that can then generalize to your cognitive performance more generally. So you become broadly more, you get smarter, so to speak, is kind of the promise. But does this really work? And if it works, does it work for everyone equally? And if it doesn't work, why doesn't it work? And what could be mechanisms maybe that we could target to make it actually effective? That is kind of the research that I'm interested in and what I want to present today. So today I want to talk first about some cognitive training studies that we did in younger and older adults. And then move on to some work that is very recent, where we looked at mechanisms of efficiency in cognitive training. And then finally, in the third section of my talk today, I want to talk about some very, very recent, currently ongoing research, really, where we look at mechanisms of efficiency in video gaming, a different type of cognitive stimulation that where we might be able to harness it for developing beneficial interventions. So I think some of you might already know about this, but just to make sure that I catch up everyone and we are all on the same page, I want to give like some background on the training and transfer theories and literature. So why would we even expect that practicing one skill could generalize to any other context? So theoretically, that is expected to occur when the trained skill or practice skill and the other skill have some knowledge components in common. So that is the common elements theoretical approach. in cognitive training research, that has then been expanded, not just to knowledge structures, but also to cognitive processes more generally. So the idea is, for example, that if you practice a task that has strong demands on on inhibitory control, let's say, as one example, and then you do a different task that might not look the same, might look very differently, but also has some requirements on inhibitory control, that then you might still do better because you have practiced before and improved that underlying process of inhibitory control. And of course, when you think about this rationale, that's the functional overlap theoretical rationale. When you think about that and you consider what would be a particularly beneficial intervention, you would try to find a basic cognitive ability or processes or set of processes that correlate positively with many other abilities so that you would maximize the possible benefits. And that is where working memory comes into place. Working memory is a cognitive system for holding available the information needed for cognition in the present moment, or in other words, it is that cognitive system that helps us to process information right here, right now. And it has been shown that the capacity of people's working memory is very strongly correlated to a wide range of other abilities, such as reasoning or fluid intelligence, attention, but then also some abilities that are more directly relevant in our everyday life. So for example, vocabulary learning at school and so on. And the idea is that if we can improve working memory and expand that working memory capacity, then we can improve all of these other abilities all in one go. So that would be a super powerful intervention because you just practice one thing and it makes you better at most other cognitive tasks. And that would be also particularly useful because often neurological conditions, for example, come with working memory impairments. And so the idea is that it could help like a wide range of people. How do we typically test whether that actually works? So typically we have like some intervention where people practice some particular working memory task or several tasks. So there could, for example, be the NBAC task, let's say. And then before and after training, people do a pre-test and a post-test. And for pre-test and post-test, we typically measure whether there is some generalization, at least to untrained tasks, that measures still working memory in this case, or the same ability as was trained. We would call that near transfer. And for working memory, you could, for example, use then the complex span, which has a quite different structure than the NBAC, but still is supposed to measure working memory. And the hallmark of cognitive training effectiveness then would be, do we see like some really broad generalization, and that is what we call far transfer to different but related cognitive abilities, let's say fluid intelligence, for example, and we would then measure that with a task that measures that particular ability, let's say metrics reasoning in this example. But does this actually work? Does working memory training expand the cognitive capacity? We did a couple of studies, that is how I started with my PhD, really, with working memory training. And well, there were some promising effects in the beginning, but then I couldn't even replicate myself, my own effects. So I wasn't sure what is going on here. Like after 4 studies or so, we had quite a balanced picture. And then when you look into the literature though, and you look at some of these many meta-analyses that came out over the last couple of years, you will see actually this is quite reflective of how the field looks overall. So this is just like one kind of selective sample, of course, of meta-analyses that are out there. There are very many meta-analyses on cognitive training and especially working memory training, but it's relatively representative, I would say. So for every meta-analysis that comes out that shows some small but still significant effect, there will be another meta-analysis showing no, there is absolutely no effect. And then it goes back and forth, and the next meta-analysis comes out showing like, no, there is some effect. So what is happening here? Why is this so inconsistent still after so many years now? Well, there have been a couple of issues, especially methodological issues, that have been discussed quite heavily over the last couple of years. And I'll go through some of them here. So one of them is that is quite still pervasive, I would say, or still something that is still quite discussed, is the lack of active controls. So those are groups that do the pre-test and the post-test, and then some alternative intervention in between that should not rely on the same cognitive processes as the active interventions or the experimental group, what they do. So for example, working memory training, you would want to have an alternative intervention for the active control that does some tasks or so that do not require as much working memory. Active controls are great because they control for not only for test-retest effects, but then also for placebo and expectancy effects. And so without having an active control, that's really problematic because you can never tell any effects that you see just due to placebo and expectancy effects. But then even if you have an active control, it's really hard to tell whether this was an appropriate or adequate control, because either they might have like an intervention where it's very clear to participants that this is not really that intervention that is tested here. It depends a lot on how you recruit participants and so on, what they will have like as beliefs when they come into the study. Or you could have an active control that also trains without, like unintentionally, the same processes as the experimental group is practicing, and then you might underestimating any effect. So this is like a really challenging issue in this area. Another problem that has occurred in many studies is that many studies have used only single ability indicators or single tasks to measure the whole kind of ability that we are interested in knowing. So let's say we are interested whether our working memory training can also improve inhibitory control, let's say, and we use only the Stroop task to measure inhibitory control, then any presence or absence of an effect could be due to just using that Stroop task. So the Stroop task could just not be sensitive enough, or if we see an effect, it could be that it is very specific to the Stroop task for whatever reason, I don't know. So what we should ideally do is use several tasks to measure an ability, so to be able to see whether there is an effect or absence of an effect across the board, across several tasks. But of course, that comes with the challenge of that you have to have long test batteries, and you might then have learning effects and fatigue effects within the test batteries and so on. So there's not a perfect way to do this, but just using single indicators is quite problematic and could have contributed to these inconsistent effects that we see. And finally, group sizes are often just very small in this area. And of course, that is understandable as well, because these studies are super, super effortful. So anyone who has ever done a cognitive training study will agree, I think, that this is like really, really hard work, starting from recruitment to actually doing all the testing to keep people committed to your study and so on. It is not something that you just do like on the side. So many studies have relatively small group sizes, translating into relatively low statistical power, which of course comes then with an increased risk of false negatives, as most of us probably are worried about, so that you might not detect an effect that should actually be there. But it can also come with false positives, so fluke effects, right? So effects that are not really there, but because you have a small sample with low power, p-values will be all over the place, and it can just happen that you have a significant effect, even though there is no true effect underlying it. And in any case, low statistical power has been shown to inflate effect sizes quite remarkably. So there has been some simulation studies that showed that if you have low statistical power, that sometimes your effect sizes might be just twice as big as the true effect would be. And of course, those inflated effect sizes, false positives and false negatives, and all go into those meta-analyses. And then maybe it's not so much of a surprise that they are not so super consistent, because it's just a lot of noise out there. Well, in this first section now of the empirical studies that I want to present some studies that we've done a couple of years ago, where we try to address these issues as best as we could. So we did 3 studies, one with younger adults, one with older adults, and then a 3rd study where we used the training data from those first 2 studies to look into individual differences, whether individual differences in people would predict those training gains that we've seen. We tried to do a study that was theoretically informed and used robust methodology relative to previous studies to gather some more unambiguous evidence, I would say, so that we could maybe draw some firmer conclusions. So first of all, as was standard in the field at the time, we did some relative intensive cognitive training. So participants did 20 to 25 sessions over the course of 4 to 5 weeks, where they practiced 3 to 4 tasks each. We tried to really power this as well as we could with the resources that we had. So our group sizes were on average around 65, which was about 3 times as big as the median group size in training studies. And we followed RCTs, or randomized controlled trials standards, by using an active control group. They practiced visual search, which has been shown before not to be too much related to working memory. We used random group allocation, and we conducted the entire studies double-blinded. So neither participants nor experimenters knew who was in what group. And finally, we used multiple indicators. So we used 3 to 4 tasks to assess each ability so that we could get a sense of whether any absence or presence of effects was across the board or was maybe specific to some tasks. Yeah, these are the results already from the first study that we did. So that was spearheaded by Carla De Simoni, who was a PhD student at the time. And here I'm showing you the results of our overall 3 groups, 2 working memory training groups. We had one group that practiced binding in particular. So that is trying to memorize and recall not only the items or some items by themselves, but items in their specific context. So that could, for example, be an item and its specific serial position, or it could be an item and its another element that it is paired with, or it could be an item and a specific location on the screen, for example. Our second working memory training group practiced updating, where we focus a little bit more on the executive control component. And in updating tasks, people have to keep track on a continuous stream of information and have to replace now no longer relevant information or now irrelevant information with new information that will now be relevant. So you have to constantly kind of keep on track of that information stream. And we compared those 2 groups to a visual search group. And what I will be showing you here, I try to get my laser pointer going. Yes. What I'll be showing you here are the gain scores from pre-test to post-test. So the higher they are, the more improvement from pre-test to post-test for our 3 training groups on the trained tasks. So these are just single bars, but those are just for illustration purposes. Those are composite scores across 4 different tasks with 4 different types of materials. So visual, spatial, verbal, and numerical. And the white bar is our control group, the active control that did visual search training. And as you can see here, for example, that our control group did improve more than our binding and updating groups in those tasks that they actually practiced. So this is what we would also kind of expect. They practiced this for 4 weeks, so they should get better in this. Our working memory groups even got a little bit worse. And the difference here between the visual search group and the other 2 groups has very strong Bayesian evidence also suggesting that there is a positive effect, so a positive difference here. So how does this look like for our training group? So for binding, we've seen that the binding group also improved very, very much in those tasks that they practiced with very decisive evidence here. However, we didn't see any transfer relative to the visual search group in updating tasks. So we found here a Bayes factor of 6 in favor of the absence of an effect. That means that even though they practice something that is supposed to measure exactly the same thing as the updating tasks, just a slightly different aspect, but everyone, I guess, would agree that binding and updating both measures working memory, they did not show any generalization of these large practice effects. And the reverse kind of mirrored pattern was observed for the updating group that also improved a lot in the trained tasks, but not at all in the binding tasks. And that is particularly impressive, maybe more like a astonishing, I would say, because when we did a confirmatory factor analysis with the pretest data, we found that updating and binding on the latent level were correlated at 0.75, and at post-test, they were even correlated at 0.91. So they're almost the same thing, right? These two latent factors, and still there was absolutely no transfer relative to a control group that trained something that was uncorrelated, pretty much uncorrelated to binding and updating. Well, now you could, of course, say, well, you tested young adults, so they were at a peak performance, so there is just no room for improvement. Maybe you should have just looked at a different population. And this is what we did. Oh, I forgot to say, we also didn't find any far transfer. I skipped that slide, sorry. Yeah, we also didn't find any far transfer in these other abilities, except we found only ambiguous evidence for processing speed here, where even though we had these large group sizes, the evidence was ambiguous. We had a base factor of 1, which means like we could have just tossed a coin instead of doing this big study to see whether there is a processing speed benefit after working memory training. And this could be because maybe visual search training also practice speed as much. You can see that there is like a large gain score here as well. Or it could be that maybe this differs for different people. And this is something that we are currently following up on in a processing speed training study that we are currently running and hopefully be presenting next year sometime at Psychonomics, at the Psychonomics meeting. But now I get to my next point that I wanted to make, and that was about our study with the older adults, where we tested whether maybe in older adults where there might be a little bit more room for improvement in working memory, whether we would see any effects here, but the same pattern occurred. So we have like large training effects here with decisive evidence that people improved in those practice tasks, but no evidence or even evidence against any effects on any of our near transfer tasks. So those were also working memory tasks that differed pretty much only in the types of stimuli. So in this study, participants practiced an updating, a complex span, and a binding task. And for near transfer, we used very similar tasks, just with different stimuli. And there was no evidence for any improvement here, and also not in reasoning, shifting, and inhibition. Well, another question that then might come up is like, well, maybe, is it possible that people are just differently or differ in how prone they are to show such transfer effects? And that some people just benefit more from training than others, and that might maybe also contribute to these inconsistent results that we've seen in the literature. So what we did here is that we used the training data from these two studies of younger and older adults and ran them through a latent growth curve model where we wanted to see who gains most from training. So what we did here is that we created several parts or parcels of the training interventions. So the first part are the first couple of training sessions, then the next couple of training sessions in part 2, and so on. And then the final couple of training sessions are in part 5. They all load on a latent intercept factor, which represents pretty much the initial performance at the beginning of training. And they also all load on a latent slope factor, which represents the increase or change over those different parts of training, so over the training sessions. And what you can then do is like you can correlate intercept and slope and see who is gaining more. So those people who start off lower in the beginning of training, are those the ones who will gain more? Those would be compensation effects, or are those people who already start on a higher level, those that gain most, and those would be magnification effects. You can then also use any types of maybe pretest measures that you have of personality characteristics, for example, and predict both the intercept and slope and see to what extent do these characteristics predict training gains above and beyond of how they predict the intercept or the initial task performance. And we had a wide range of measures that we just ran during pre-test. So we had like a whole set of questionnaires, including the big 5 personality factors, for example, motivation, cognition-related beliefs like theory of intelligence, grit. We also had demographics, of course, age, gender, things like that. And well, what did we find? Well, we found, first of all, cumulative benefits of initial task performance. So that means that those participants that already started on a higher level, those were the ones that gained most during training. So those are like the magnification effects that I mentioned before. And you can think of this as richer, the rich become richer. So those who are already good at it, those are the ones that gain most. And very much to our surprise, we didn't find any single participant characteristic or variable that predicted the slope reliably in a direction that makes sense. And so there was like one exception where theory of intelligence predicted it the other way around than what you would expect. So people who believed more in that intelligence is fixed, they showed a little bit more of a training gain, but that was the only one, and it was only in one age group. But other than that, across the board, and we had 28 variables, there was absolutely nothing that predicted the slope above and beyond the intercept. So whether people were more or less motivated, for example, more or less open, and so on, it did not really matter all that much. So we were quite surprised because we thought, oh, this is it. People just differ in how prone they are to gain from training, and that must explain it, but it did not. Well, to give like a first kind of interim summary at this point, what we found across these 3 studies was that there were very reliable, robust, large working memory training practice effects, right? But they did not generalize at all to working memory capacity in a broader sense, because we didn't find any near or far transfer, neither in younger nor older adults, even though our near and far transfer abilities were very, very strongly correlated, even on the latent level. We also didn't find any correlations of individual differences in motivation, personality, or these cognition-related beliefs. So what we concluded from this set of studies was that, well, working memory training is definitely no quick fix solution for reliably boosting working memory executive functions and intelligence. It seems to work from time to time, but it did not work in a way where you would say like, okay, this is something that you can sell to people, right? As like that kind of solution for cognitive impairments. Still, I think it is really interesting that people gain so much during training. They get so much better, independent of their age, for example, and their socioeconomic background and so on. So it seems like people really, really pick up something during working memory training, and their performance is way beyond of what we would usually expect to see in working memory tasks. So we were wondering what is actually happening during training, and is there maybe still something that could be harnessed in future training interventions? And so first of all, we kind of looked into what do people actually do. So we just asked them after the training intervention, what kind of strategies did you use, if you did use any? Not a great way to measure this. It's very complicated to measure strategy use. Like in the there is no perfect way to measure it, but that was like one first kind of step that we took. And what we found was that more than 80% of trainees reported to use some strategies. So almost everyone does it. People kind of do a task that is really hard. It's adaptive, right? So the better you get, the harder it gets. And so you are or most people are trying to find some ways to reduce that cognitive effort they have to put in. And we interpreted it as, well, as we did not see any evidence for transfer, it seems that that using some strategies doesn't really help you with your capacity. You know, it won't expand your capacity, but it clearly increases the efficiency with which you use your capacity by figuring out how this paradigm works. How can you, so to speak, cheat the paradigm? And we call that the development, or we label that the development of paradigm-specific expertise. And what did people then improve in? So we did a little bit more digging into the specific data that we had from the training tasks, and we analyzed the distributions of errors and so on. So what did people actually do in these tasks, and what kind of aspects did they improve in? And we found that both in the binding and in the updating groups, they improved in just remembering what kind of items they have encountered in that trial, but without the specific context. So for example, if they memorized a list of, let's say, 5 letters, they were able to recall those 5 letters in any kind of order, but they did forget at what kind of specific position each of those letters were. So you can think of this as they improved in their familiarity-based processing, but not in their recollection. And that is something that we certainly kind of did not hope for, because like when you think about what is working memory, you would think that this kind of binding between those items and their specific context, that is kind of really core to working memory capacity. So you would want them to improve in that, but that is something that they just did not improve in. They very clearly improved only in the memory of the items themselves. And we interpreted that as maybe some evidence for increased efficiency of using the available capacity through acquiring stimuli-specific expertise. So it seems like somehow they kind of got really familiar with these types of stimuli that might have helped them to maybe discriminate them better or something, and then just know, oh yeah, this one was in the trial and this one was not, but I have no idea what its specific purpose was. Well, and these results and like the findings that we had from the previous years, and of course the findings of others in the literature, motivated us to think about, okay, what could maybe be happening during training, and how could we maybe come up with a framework that might help us to think a little bit differently about these results, rather than just, yes, there is an effect versus no, there is no effect. Are there maybe different pathways how training could work? And that led us to develop the capacity efficiency model that we just recently published in a recent review article, where we proposed that training can affect possibly, maybe, capacity, but certainly efficiency. And to explain a little bit more about this, so with capacity, what you would think when training improves capacity, that means like that the overall kind of cognitive capacity or resource that you have available really expands. And when you think about a problem, maybe as an analogy about the problem that, that you want to lift really heavy weights, if you would want to increase your capacity to become better at that, you would increase your mere muscle mass, kind of. And in comparison, if you improve your efficiency with which you use that capacity, you wouldn't bother too much to increase your muscle mass. You would rather think about, okay, how can I more, in a smarter way, use what I have already available to do the same job? And you might come up with the idea to just use leverage instead. And that might be happening during training as well, that people, to kind of avoid that cognitive effort, they come up with clever ways how to use what they already have in a more efficient way. And when we think about these two pathways specifically for working memory, this might look like the following. So for enhanced working memory capacity, if it would happen, we would assume that people would be able to hold available a higher quantity of representations. That should then induce really, really broad transfer. But for an enhanced working memory efficiency, we wouldn't expect there to be like much of a difference or change in quantity of representations, but in the quality of the representations that people have. So they might be able to hold just the same really number of representations, but they would be able to hold them in a way that helps them to better recall them more reliably later. And we think that there are different kind of aspects to this. So one is paradigm-specific expertise, the other one stimuli-specific expertise that I just mentioned before as potential mechanisms to enhance working memory efficiency. Another way could also be to learn how to more efficiently allocate attention. So for example, when you think of dual task situations or task switching situations, when you figure out how to be a bit more clever about how you allocate your attention, how you kind of get the task to do it in a better way, in an easier way, you could maybe use that then also in other contexts. And that is the thing with this, with capacity versus efficiency, even though transfer might be much more narrow after when you only enhance efficiency, it could still maybe induce transfer either to contexts that really make use or offer kind of some opportunities to use that paradigm-specific expertise or that stimuli-specific expertise, or if you help people to kind of recognize that, so maybe give their metacognition a little bit of a boost to kind of tell them, well, you can use what you've learned here in this and that way, in this other context. Well, yes, so in the next section of my talk, I want to talk a little bit more about a study that we've just very recently completed, where we zoomed into this paradigm-specific expertise and stimuli-specific expertise to test this a little bit more directly. So this is a study that is spearheaded by Shanke Chang, who is a PhD student in my lab currently. And she did this online training study where she investigated training effects on working memory representation. So what participants had to do here was an orientation reproduction training, where we presented triangles with different orientations, and participants had to memorize those orientations and then reproduce any of those orientations with their mouse by kind of turning it around and then clicking to say, okay, this was that particular triangle. And in this setting, what we could potentially see is that participants might enhance their capacity and remember a larger number of such orientations. So let's say maybe at the beginning of training, they were able to remember and recall or reproduce 2 orientations. And then maybe after training, they would be able to do that for 4 triangles. Maybe those orientations might not be super precise, but they might get like, the general direction right. Or alternatively, or maybe also, it could enhance precision instead. So people might still be able to just remember 2 orientations, but in a much more precise way. So now they might be able to get it really almost exactly right. So they might remember fewer representations, but with a higher quality. And this is what we looked at in this study. So here we had 30 participants in the experimental group. We compared them to a visual search group of 34 participants. They did 4 sessions of training. Each training session was 30 minutes of either that orientation reproduction training or a visual search training. So similar to what we did in the studies before. However, this time we looked specifically at whether any kind of development of expertise for those specific stimuli or the specific paradigm might transfer to other contexts that might offer opportunities to actually use that expertise. So we had one transfer task, the shape reproduction task, that used a similar paradigm. So people also had to reproduce with their mouse the stimuli, but it was different stimuli because it was like kind of donuts that they had to reproduce. And we also compared performance on the orientation change detection task, which is a different paradigm. So here you have to compare 2 arrays of stimuli where there might be a difference in the direction of one of the triangles, or they might be exactly the same, and you have to tell. So it uses exactly the same stimuli. So we thought, okay, if they get really super familiar with those triangles, they should still become better also at orientation change detection. Well, what did we find? Well, we found that our participants actually did all increase their capacity from pre-test to post-test. However, both groups improved just to the same amount. So there was no interaction effect here, and we found Bayesian evidence a Bayes factor of 4 in favor of the absence of an interaction effect. However, for precision, it looked differently. Here, our control group even decreased a little bit in the precision with which they could recall those orientations, and our experimental group improved, and the evidence for this was quite decisive. So we found very strong practice effects in the trained tasks on precision, but not on capacity. But did we find any transfer to the same paradigm, different stimuli, or or the same stimuli in a different paradigm? No, we did not. Our effects were super specific, right? Just to this orientation reproduction task. There was no transfer, although the evidence for the absence of these transfer effects was rather ambiguous. So there could be maybe we had still too few participants, or maybe our transfer tasks didn't really pick up on possible transfer, or maybe some people showed some transfer and others did not. We do not have the sample size here to really look into the individual differences as much. But there were no kind of, tendencies that would make me think, oh yeah, there is like, a lot to it. Instead, what we did then was we digged a little bit more into what did people actually respond in these tasks. And that was quite interesting, I think. So what we found here was that participants showed at pretest here for our active control group and for experimental group as well, what we found was that participants had very specific kind of groups of responses they gave. So the responses are here down there as a degree. So that is kind of the orientation that they choose. And so it looks like that was not a uniform distribution here, right? So there are like some peaks here that suggest that people thought about these orientations in kind of categories. So maybe they use something like a clock face or so as a memory aid. That could be that they had like, okay, this is like roughly 12 o'clock, this is roughly 3 o'clock or something. But then at post-test, while the active control group still showed pretty much the same pattern as they did at a pre-test, the experimental group very clearly developed a flatter probability density curve because they had developed more peaks, so to speak. So what we think what happened here is that through training, they got more familiar with these orientations because they were working with them a lot. And so they were better able to discriminate on a more fine-grained level between different discriminations. And they maybe discriminated not just between 12 and 3 o'clock, for example, on a clock face, but between 12 and 1 and 1 and 2 and so on. And the evidence for these two distributions to be different at post-test was, again, very strong. So how we interpreted that was that this might be tentative evidence for an increased use of such canonical orientations after training. And we think that could suggest a possible interaction between developing that paradigm-specific expertise, so figuring out some strategy to do the task better, using a clock face as a memory aid, for example, and the development of stimuli-specific expertise. So being better able to discriminate between those different orientations of triangles. So getting like a more, really a more precise representation of those. Well, just to give like another summary very briefly of this study. So we feel like this is nice kind of first evidence that cognitive training can affect these mechanisms of efficiency. And that we found that these improvements in visual working memory precision were very paradigm and stimuli specific. So there was just not enough there for transfer. They may have interacted to further boost performance, and they were possibly related then to strategy use that we might have, that we did observe in other studies before. So yeah, so this is definitely something that I find super interesting, and I hope that we will definitely investigate that further in a couple of next studies as well. So now for the third section of this talk, I want to move on to a different area of cognitive stimulation, which is video gaming specifically, and see whether there are maybe whether video gaming can maybe improve some mechanisms of efficiency that might then be harnessed for developing interventions. And video gaming in particular is so interesting to look at. Also because there has been lots of research showing that video gaming performance can correlate with cognitive, not performance, but video gaming habits correlate with cognitive performance, and video gaming training studies have shown sometimes to show some positive effects as well. And what people often say is that, well, this might be because video gaming compared to our typical cognitive paradigms are so much more fast-paced, exciting, interesting, and they have lots of more kind of visual and other sensory information kind of, being thrown at you. You have to integrate all of that information, and this kind of multisensory experience that could maybe boost cognitive performance more so than just using single paradigms. So in this line of research that is spearheaded by Eleanor Hyde, who is another PhD student in my lab, and where we collaborate with Endpoint, which is a professional esports team that happens to be in Sheffield as well. We look specifically at playing CounterStrike. So why are we looking specifically at CounterStrike? Well, this is an action video game, a first-person shooter that is particularly interesting because there is so much going on that could potentially boost cognitive performance. So for example, in this screenshot here, you would be the player, this would be you here, and you would be playing together with 4 other people in your team. And you would have to make sure that no one gets onto the site here. So let's say you try to kind of keep this clear, right? And you could now have like other players from the enemy team pop up, for example, here or here, coming from here or from there. And you have to kind of look at all of these different locations simultaneously. And so there's a lot of kind of, attention shifting going on, but then at the same time, also, it's not only your visual attention that you have to, focus on the scenery. You also have to listen really hard, whether there are like some footsteps maybe that can give you some additional cues. But then there is also your teammates, right, that could tell you and give you like some information of what is happening at other sites in the game. So you have to integrate that information as well. And sometimes you might have teammates that are just cursing around and distracting you all the time, and you have to suppress that as well, right? So there is a lot going on at the same time. And once you have integrated all that information, you have to draw some conclusions from that and make a very fast reaction, because this game is really fast. Once the action is happening, it happens really fast. So this could be really interesting. Another reason for using this particular game is that it's pretty much free to play, and it's played by a lot of people around the world. So it had like a big peak during the pandemic, but it's been around also already for a very long time. So the first version came out sometime around 1999 or 2000, and people are playing it ever since. It's getting only more people. So you have like very young players, but then also players that are at least middle-aged, if not a bit older as well. So you have a little bit more of a range than with many other games. Also, because it is for free and it's a global game, you have people from all sorts of backgrounds and different countries and cultures, which makes it a very interesting setting as well. So what did we do in this very first study, which is just the first exploratory kind of step to kind of get into this area of research? We did an online study here with 235 CounterStrike players, and we asked them to do a color shape task. We measured with that processing speed, also task mixing and switching, but because I'm a little bit low on time already, I will just skip task mixing and switching because there was nothing there. I can show you later if you're interested. But what they did in this task was they had to, they were shown stimuli, abstract shapes in either green or blue, and they had to decide whether that was a green or blue stimulus, or whether it was a curvy or spiky stimulus. And we had single task blocks where they just did color or just did shape. And we had a mixed task block where they had to switch between determining the color or the shape based on a cue. So here, what I will present today, I will show you the data from the single task blocks. And after they did this task, which is very different from what they usually do in the game, they did complete a CounterStrike survey. And this survey we developed together with CounterStrike players and with professional players from Endpoint as well. And here we looked at a whole range of different variables. So as I said, this is quite exploratory work. So we are just trying to figure out what are the best variables here to use. But in the end, we felt we identified 4 that are very promising. So that are the total hours of playtime and the weekly hours of playtime in CounterStrike. And we have quite precise numbers for that. And that is very cool about this as well, is because CounterStrike is a game that is played through the platform Steam, and Steam logs all the playtime. So people can just look up in their Steam account, what is my actual number of total hours over my entire playtime, and how much have I played over the last week or so. And so it's not just like a self-report itself, like, you know, estimate that can be prone to biases, but you have a really relatively good number there. We also use the current ranking in the game. So this is correlated roughly with skill level. It's not really the skill level, and it's a proprietary algorithm, so we don't really know what it exactly measures, but it gives like some idea where do people stand relative to other players. And we asked them to also self-rate their expertise in the game. So where do they think they stand? And then we ran a k-means cluster analysis to have a data-driven, purely data-driven approach to see, like, do people cluster around using these variables? And we found like that there was the evidence was strongest for forming 4 groups of CounterStrike experience or expertise. And based on these 4 variables, and because these are 4 variables, you see 2 3-dimensional plots. So we have here the self-rated expertise, the weekly hours of playtime, and the total hours of playtime. And here you see also the total hours of playtime, weekly hours of playtime, but then the current ranking instead of the self-rated expertise. So you can think of this a little bit like this is the subjective ranking, and this is the more objective ranking. And what we found was that those 4 groups how we interpreted those four groups, I should better say, is that we have like this yellow group down here. We labeled those the casual players. So these are people who don't play as much on a weekly basis as others do. They have not all that much total hours of playtime. They also don't rate themselves as very good players, and they also are not that well ranked. I should say, though, that these people here, even those casual players, they have like often around 20 hours of playtime per week. And many of them have about 3,000 hours total playtime. So when you compare that to the typical video game training intervention, that's a very different scale. So in the typical training intervention, you would have maybe 20, maybe in good studies, maybe 50 hours of training time. But 50 hours is like maybe 2 hours of a casual player playing the game. And then we have what we call the experienced players, the pink group. So they consider themselves as better players, also rank a little bit better. They have more total hours of playtime than the casual players, but also play, well, casually, you would say. So they don't play all that much during a normal week. And then we have the blue people here that we label the aspiring players because they seem to grind a lot of hours playing the game. So they have sometimes like a full work week, sometimes more like, 60 hours per week or so that they play this game. And we interpreted that as, okay, they really want to get better or so. And they are a little bit all over the place when it comes to the ranks and the self-rated expertise, but their total hours of playtime is still relatively low. I say relatively low because it's not super low, but it's much lower than our final green group. Those are our semi-professional and professional players who have like loads of total hours of playtime, often play a full work week because they are professionals, so they do this for their job. And for example, here our most experienced player had 13,000 of total player hours, and lots of them have around 10 to 12K. So we then looked at these 4 groups and how they did differently in our processing speed task. And this is what we found. So these are some preliminary results, kind of hot off not the press, but the analysis tool. And what we found was that our semi-professional and professional players, as well as the more experienced players, were definitely faster than the other groups. So there was a significant effect here, but in accuracy, they were all still the same. So they were very fast, but they kept the same accuracy level. And that by itself is quite interesting and nice to see. We didn't see any effects here, as I briefly mentioned before, in task mixing or switching. But overall, they were faster. But what does that actually mean? Why were they faster? Were they faster really in this kind of decision-making process, or were they faster in just clicking the mouse, or what is it really? And to get more information about that, we subjected the data to a drift diffusion model, where we can look at different components of the reaction time distribution. So we can look at the actual decision-making process, so the drift rate with which participants arrive at one of the 2 possible options of the task. So for example, say whether the shape is curvy or spiky. We can look at the boundary separation, which is the strategic component. So people can have very narrow boundaries and, for example, focus much more on being very quick, or they can have very wide boundaries and say like, okay, I really want to get this right. So I'd rather wait until I'm really sure about the accumulated evidence that I have before I make a decision. And we can look at the non-decision time. So that is some encoding processes mainly that happen here, and mainly the motor response that can happen here. So are they really just much faster in pressing the mouse, for example, clicking the mouse, because that is what they do all the time. And this is what we found here. So we found that there were some differences for drift rate. So there was a group effect. It was not entirely clear where the group effect exactly sits. There was on average, the semi-professional group had a better drift rate than the other groups. The experienced players also tended to have a better drift rate than aspiring casual players. But as you can see, the drift rate distribution here for our semi-professional group is very, very flat and wide. And that could maybe be because we use the data-driven process of the cluster analysis. So we can't really tell who are really the professional players and who are not. So it might be that maybe those on the lower end are actually more players or people that happen to fall into this cluster using the data-driven approach. And these might be more our professional players or not. We can't really tell based on this data. And this is something we want to look at in some future studies. But we did find some expertise effects on drift rate, which suggests that there is something to a higher efficiency in evidence accumulation in those more experienced players. But we definitely want to dig deeper into this. In contrast, when we look at boundary separation here, so the strategic component, we did not find any differences between groups here. But what we did find was that our semi-professionals, that they had indeed shorter non-decision times. So there is something to the idea that they are just faster at encoding and clicking as well, but that's not the entire story. So there is also something to their decision-making process in addition to that. Okay, so that brings me now to the end of the research that I wanted to present today, and just for a brief discussion of what I presented. Across those different studies that we did, and coming back to the capacity efficiency model, I would conclude that there is really very little or maybe even no evidence for actual experience-based plasticity of the capacity of working memory in particular. So I've shown you 3 studies where we looked at this. We also did another study that I was involved in with Samsat Himi recently, and with Isabel Ripp as well, where we looked at at multimodal neuroimaging, for example, and we didn't find any evidence for any capacity-like improvements. So what I would conclude from that is maybe we can kind of, we shouldn't kind of bang on trying to get people to enhance their capacity and with that just improve everything. But instead, maybe it might be more valuable to actually embrace that efficiency mechanism and to look more closely into that and investigate that instead, as there seems to be good support that cognitive activities such as cognitive training, but then also video gaming might support the development of this paradigm and stimuli specific expertise that might be very specific to one context, but maybe we can harness that and help people to use what they've learned in one context in another one. So we found specifically that people developed a higher precision of their representations. I showed you the research from Shankar Jang. I have another PhD student in my lab, Chris Billy Arianto, who is looking at musicians and why they often show better working memory. And it looks like there is something going on with auditory sensory discrimination that also speaks for higher precision of representations in those with more expertise. And the other part of evidence that I presented today is that people with more experience with specific cognitive activities, here for video gaming, show better potentially better buildup of probabilistic inference. So in Eleanor Hyde's study, but we also have another study that we just submitted recently by Alice Reinhardt, who is a PhD student at a medical school in Hamburg, working with Thilo Strohbach, a collaborator of ours, where we looked at processing speed training and found that people can improve in the drift rate when they practice processing speed. And we have an ongoing study right now where we are looking into whether that kind of processing speed training, if it improves the drift rate, whether it can then maybe also improve performance in other tasks that rely also on drift rate. Well, and yeah, for the next steps, I think what would be really good is to identify these mechanisms of efficiency, figure out how they really work, and then see whether we can use them to develop these really powerful interventions that could be maybe more reliably effective. And this brings me to the end of my talk. Thank you very much for attending, for being here, for spending your attention on this research that I'm so excited about. Thanks to all the collaborators that that contributed to this research. And then last but not least, to all the fabulous students in my lab. Thank you.
Thank you so much, Claudia. I appreciated the talk. Very engaging. I love the 3 parts. It was nice and easy to parse as we went through. So several individuals have included information or questions or comments throughout the talk. So I will just kind of address them as they go. And I think that they kind of align really clearly with your 1, 2, and 3 interim summary pieces. So Alan Dunn asks, has anyone tried to chart the distribution of effect sizes of those trainings that you talked about in the first section?
Sorry, can you say that again?
Has anyone tried to chart the distribution of effect sizes of those training interventions?
The distribution of the effect sizes. Yeah, I mean, like, I guess you would see that in most meta-analyses, like the distribution of the effect sizes across several studies. I try to think off the top of my head whether, like, what is the most common picture. I think there is definitely quite a bit of heterogeneity going on. So that is why I think, even though on the meta-analytic level, it's like often like, okay, there is a small but just significant effect, or no, there is no effect. Often it's like that the average effect sizes may be relatively similar, but then it depends on how much heterogeneity is there, whether it gets significant or not, and so on. And in some studies, you can really see that there is quite a wide, in some meta-analysis, you can see there's quite a wide range of effect sizes. What kind of makes you think, right, why is that the case? So are there specific studies that might have just gotten it right, or is it really just noise? And I think up to this day, we still don't really know what the reason for that is.
Thank you. So Tom Carr, who asked quite a few questions, he was super engaged in your talk, so I assume that means he was really into it, asked basically a follow-up on the evidence of negative transfer in the visual search group from cognitive training. And he wants you to talk a little bit more about that negative transfer.
So that is the negative transfer from the working memory training groups on the visual search tasks, I guess, for the first study by Carla De Simoni. Yeah. So it's hard to tell really what that means, right? So it could be that the working memory training tasks just made people focus on different aspects of tasks that were not as useful in this particular task as much. So, for example, the working memory tasks had emphasis very clearly on accuracy, right? So feedback was an accuracy. That was the same, although in the visual search task, but in the visual search task, you would always get it right eventually, right? So that was like a race on the screen. You had to kind of go through in a sequential manner through the screen until you find the odd one out stimulus. That was, for example, a 3 amongst 8s or something, and they were all tilted. So it was quite hard to find it when you had lots of them on the screen. So there you would always eventually get it right. So probably what I could imagine what people might have done is like just, you know, focus a little bit more on getting this done faster and getting through it faster. As in the working memory training tasks, the emphasis was so clearly on accuracy because you would get the feedback on whether you got the item right or not, for example, at the right position and so on. So you would probably not care too much of things like reaction time and getting it right faster. So maybe there is some that has something to do with that, why we see some negative transfer, just because working memory training might have not emphasized on those, on those aspects of the task that would have been useful in the visual search gain score. So
makes a lot of sense. Yeah.
Could also be noise, obviously. That is always the thing, right? There's always also that possibility. We just lose Dawn. Possibly. I might just try. Ah, there she is. Did we just lose you?
Sorry. Yes, something just happened. Everyone froze and then I went away. So no, I don't know if you heard the question that I was posing from the Q&A. It was about the individual differences. So someone asked if you can explain how intelligence and other cognitive abilities didn't predict the slope, even though their efficiency was improving. And perhaps could that be because it's hard to isolate efficiency?
Yeah, so we did not try to use those other abilities to predict the slope. We only used participant characteristics from the questionnaire data that was like kind of separate. And so for example, things like age, gender, socioeconomic background, motivation, as with the intrinsic motivation inventory, grid score, theories of intelligence score, things like that. Neuroticism score, for example. We didn't use intelligence. I'm trying to think whether I could still say something to that, because like in a different study where we used also that data from De Simoni in a study that Nachshon Mehran was first author on, he modeled that data and some data from his lab, where we looked at the question whether acquisition of strategies during training could actually hinder your transfer, because you're then so focused on getting this particular paradigm right that even if you improve your capacity, you might then still not be able to show that transfer, because that kind of strategy use hinders you from or prevents you from that. And so what you would then assume, what you would see is that if people acquire these kind of strategies, that performance in the beginning of the training intervention in the first session would be very strongly correlated with performance in the second session with the third, and so on. But the more distance you have between the sessions, the lower the correlation. So you would see like a simplex kind of pattern there. So for example, performance between session 1 and 5 would be less strongly correlated. And we did indeed find that in both of our training studies, that it seems like, yeah, indeed, the working memory training task in the beginning of training seems to measure something different than at the end of training, because the correlation goes down. However, we modeled also a fluid intelligence or reasoning factor from the pretest data that was like separate from the training data, and looked at how training performance would load as a function of training session on that reasoning factor. And we found that, so you would assume then that that loading would also go down over time, right? So you would think, oh yeah, you don't show the transfer because in the end you don't do the working memory task like a working memory task. So you would think that the working memory training task loading on this separate kind of external fluid intelligence factor should reduce over time. But we did not find that. So in Nachshon's training data, it was just stable over time. But in Kala and my data, that loading even got up. So it even increased. So by the end of training, whatever people did in the working memory training task then, which was not correlated as much anymore with what they did in the beginning, was correlated more strongly with intelligence than at the beginning. So if anything, that definitely doesn't explain the absence of transfer to intelligence, I would say. It's super interesting, but yeah, strategy use alone isn't it, I think.
Very cool. That's very interesting. So more of the questions thereafter kind of dealt a little bit with the idea of the ecological validity and just this new approach to the CounterStrike lab training, right? Or standard training versus lab training. There were some questions regarding whether or not there are maybe selection effects in the sense that if it's quasi-experimental, seasoned video game players are just more likely to be faster, and the direction of causality is perhaps reversed. Faster people are just more likely to play this type of game. And then Tom, I think, is again kind of interested in that idea that you were speaking to with the standard lab training and it being a couple of hours versus 1,300 hours on astronomical numbers. So if you could just speak to the idea about how that transition is really comparable perhaps to some of the lab work.
Yes, yeah, that is super interesting and also a super important point. So obviously that study that we did there was only correlational, right? So we have no idea what is, where do those people self-select to become more experienced players? Is it like, if you're too slow, you might really not enjoy that game and stop playing it, right? And when we spoke to, people at Endpoint, at the professional team, they were more interested in the other direction of causality, right? So can we maybe, better pick people who are already better in their cognitive abilities because they might be better players then? So it depends on from what side you look at it. So correlational studies won't ever be able to, I think, to really conclusively answer that. And we just have to live with that. I think what would be super interesting is to do like a longitudinal study where you start following people who start playing, I don't know, maybe you're 16 or something, and then you do some tests over the time, and with like the information that you would have from these platforms, you can kind of really track how much they play and so on, and then kind of try to predict how that correlates with the cognitive development or cognitive changes. Still has like some issues, but that might still kind of give us a little bit more information. What I think we can't ever do is like, do a video gaming training study where we have people train for 2,000 hours CounterStrike versus 2,000 hours of visual search or something. That would be, I think, unethical at the least. But I think there will always be a little bit of that problem. What I think could be interesting though is like, if we can figure out what is really, what are the aspects of playing CounterStrike and the aspects of cognitive performance that really the core or the essence of that correlation, then we can maybe target that specifically in a training intervention and see whether there is a causality in one or the other direction. So I think it's more interesting than to kind of, harness what we could get from that. Or the other way around, kind of trying to understand how we can maybe help players then to see, oh, actually I'm picking up something from this game that could be useful in other contexts. So let's say they understand, well, I'm communicating always with my teammates, and if I'm I don't know, I have to kind of get along with them, I have to socialize with them in some way, right? And I have to suppress maybe my very negative emotions, so not to distract everyone and not to be distracted myself. And maybe kind of these kind of learned lessons, they could maybe be used as well for, to kind of help people see that you can transfer that to other contexts, even though it might not have to do with the cognitive causality there.
Yeah, your answer touched on a lot of the different kind of questions in terms of general implications, in terms of workplace training and new employees, how to go about that task. Erica also follows up to ask, one of the meta-analyses you cited showed that the largest gains in training were in those who were functioning fairly low, basically those who needed rehab. But you also showed that there is a trend across the literature of the rich getting richer, which I thought that was interesting too, the higher functioning showing more improvement. So do you think that the mechanism of improvement is different for these populations?
Could be, yes, absolutely. Absolutely, that's such a good point. So like, yeah, some of my colleagues and I, we sometimes happen to be like in the same symposium, and I'm presenting this work on, oh yeah, magnification effects, and they're like, oh, compensation effects. And it's really, really interesting. And I think what could maybe be the issue there is that maybe people who are already who are in a healthy spectrum of cognitive performance, they might show magnification effects, but people who have like a capacity impairment below below the normal functioning range or something, that for them kind of having like some intervention that kind of gets them back to that level, they show the compensation effects, but it might just be about bouncing back to the level that they have been at some point, if you know what I mean. So rather than expanding capacity. So it might be a different mechanism indeed. So not necessarily expanding it, but maybe just kind of, reinstating it maybe in people who have specific impairments.
Great answer. Alice Healy also wants to know a little bit about that and this idea of the rehab. So did any of your subjects get trained to suppress distractions? And if you isolated that as a skill, do you think it would show transfer?
Ah, that's an interesting question. Also, hey, Alice. No, I wouldn't say specifically that they were trained in it. So it was definitely part of the binding training, for example, because there we threw in some lures. So we kind of tried to trick our participants to think, oh yeah, this was like the right item, I should say yes to this. They didn't get better at dealing with those lures though at all. So even though we tried to train them in suppressing or not falling for that interfering information, they just kept on falling for it and didn't really get it. I could imagine, yeah, if you, so that would be interesting, for example, for looking at also the video gaming stuff, for example, because their suppressing distraction is so important, and maybe that could be like one of the ways how it might relate to other cognitive tasks as well. That is well possible, but yeah, we haven't looked at this specifically.
Okay, so so many different questions. I want to try to get as many of them as we can. Okay. Arthur Kramer says, thank you for your interesting and thoughtful presentation. I was wondering if you had a chance to examine changes in connectivity in neural networks of relevance to your training tasks, perhaps via fMRI, as a function of dose of training and individual differences in those behavioral performance effects.
Cool, thank you. That is a great question. Yes, we did a study, well, it's 10 years ago now, where we looked at neural networks in EEG before and after training in younger and older adults. I think we only ever really analyzed the data from the younger adults though. So, and what we found was that our training group, who did like some mix of different working memory training tasks compared to the active control that did, I think, what was that at the time? One task was also visual search, one task was a quiz, and the third task, I forgot what it was right now, that they showed a trajectory to show more of a small world network in their frontal parietal kind of areas. And so that means like the network showed larger nodes and shorter pathways between those. And what we also found, we looked in the same participants also at DTI, and we found that the white matter tracks also became, well, yeah, better is the wrong word, because we don't really know what is better when it comes to DTI, but they became more efficient, so to speak, also from the parietal to the frontal areas. But that is with the caveat that that was a relatively smallish sample size. So we had like about 30 participants or so in those groups, in each group. And we never replicated that yet. So I think it is interesting. There could be something to that, but I'm not sure, like, you know, we haven't tried to replicate it yet. In a different study with Isabel Ripp that we just published relatively recently, we looked at all sorts of outcomes. So we did multimodal neuroimaging, or they did. I was just the behavioral person involved in there. And they're across the board of so many different neuroimaging measures, we didn't find a single effect in anything. So we had fMRI, MRI, PET, I don't even remember what else. So many different things, and it was just nothing. So yeah, not so sure about it. I think probably you would have to have like very specific reasons to think that this particular task or setting or training could have, like, because it's, yeah, I don't know, has like could have a very specific effect on a specific network rather than like these very broad effects. That makes sense.
Yeah, fascinating. So the group is also kind of coming back to the idea of inhibitory control in a couple of different contexts. So I'll read a couple of questions on this theme. Vanessa Rensler asks, due to the conflicting findings on bar transfer, would you say that rehab clinicians who strive towards evidence-based practices should hold off on any type of working memory training, in that there is an oral rehab approach that involves working memory training with the idea that it improves the ability to understand speech in noise, inhibitory control perhaps? Very interesting to see what your lab finds regarding the auditory domain, and similarly with response inhibition. If there is a desire to improve response inhibition, would you recommend an adaptive repeated practice training approach in line with the commercially available cognitive training programs like Luminosity or Brain HQ, or something more along the lines of a mindfulness-based training?
Oh, that's super interesting. So I should say that I've only ever worked with healthy adults, right? So I really don't know all that much about rehab interventions or clinical interventions in this area. So I would definitely not want to say like, oh no, stop doing this, because I don't know. We did like one meta-analysis, because I had a wonderful master's student who was like super interested in interventions for dementia. And so we did a meta-analysis on different types of cognitive stimulation for patients with dementia. And I was really surprised how effective those were, for example, because I was going in with my cognitive training hat on, like, oh yeah, probably null effects, you know. But then, no, actually, there were like positive effects, and they were there for the kind of near transfer domain, and they were there for very different other domains, like especially depression, what I found super interesting. So that probably doesn't mean that really the capacity has changed again, but that cognitive stimulation could have helped to just kind of, you know, boost mood and so on, and would be super useful then specifically for those patients where other treatments of depression don't work all that well anymore. So that is like then, you know, just a different purpose of that kind of intervention that would still be super useful. Definitely something that they should then keep doing, right? Because it is helping people. It might just help them with a different aspect of their problems than what the original intervention maybe had targeted at some point. So I think in clinical settings, it's really about, well, does it actually help? And if it helps, then maybe in the next step, it's like, okay, why does it help now? But as long as it does help and you see those positive effects, I think, yeah, then I would definitely not say hold off on it.
Yeah. And then with regard to non-clinical samples, what are your thoughts about improving response inhibition via repeated practice on luminosity and brain HQ versus mindfulness-based attention training?
Yeah, that's a bit outside of my area of expertise, but like from my little bit naive reading of the area of mindfulness training and so on, I had the impression it is a similarly kind of inconsistent pattern, a little bit of findings. So I'm not too sure how strong the evidence is that it has very specific effects on specific areas, aspects of cognitive performance. I think that is often the case when that any kinds of cognitive activities or mindfulness training and so on can have potentially positive effects on, well, all sorts of aspects of life, but they might not necessarily have very reliable, robust effects on maybe Stroop task performance, right? So I would say often that is a little bit conflated sometimes in those discussions, and then people say, oh, but mindfulness is good in any case, and that might well be, but I don't know about how strong and robust the evidence is for it having like broad cognitive effects, I guess. So I wouldn't dare to say it's better or worse than repetitive cognitive task practice. I don't know whether there are many studies that have systematically compared them, and I'm not sure that the evidence base for either is strong enough to at the moment say that it's like, yeah, this definitely is something to go for with the aim to improve your cognition specifically.
Yeah. Back to the video games, Klaus Oberauer and Alice Healy have similar kinds of questions about video game effects. So Klaus writes, your results show that it takes thousands of hours of training to obtain even a small effect on reaction time. In light of that, how likely is it that these effects shown in lab experiments with training groups playing some 50 hours are even real? And then Alice follows up with, did you ever give the video game semi-professionals any lab tasks? And did they show interesting differences on those lab tasks relative to subjects who did not spend a lot of time on the video games?
Hey, Klaus, by the way, good to see you here. Yes, I agree. This is yeah, I think that is one of the things that we really noticed when we looked at this data, that is, wow, this is a much, much, much bigger range even than we thought. So this was one of the reasons why we wanted to work specifically with actual players that are habitually playing, because we were thinking that also based on our own experience that 50 hours of video gaming is like not all that much. That is a couple of weeks in and that's it, right? So why would that change substantially, fundamentally your cognitive abilities or performance? It might maybe just starting something new might have some effect, but how fundamental can that be? Otherwise, our cognitive system would constantly completely change just from, I don't know, trying a new recipe or something when cooking or so. So it's like, yeah, I agree. It's like it makes those effects coming from those training studies look a little bit like, how strong can they really be? But I think the most robust effects that they showed were more in the visual domain. So things like visual acuity and so on, which I could see like, okay, there it might make more sense that you might see some effects already from just maybe 50 hours or something, because they are much more specific compared to effects on your general processing speed or your general working memory or something like that.
And so to address, again, Alice's idea, are you bringing any of these semi-professionals into your labs?
I would love to. Yes, yes. So if any professionals are here, please come to our lab. You can also test you online. Yeah, so definitely that is something that we want to do. So we have we have so many ideas what we want to do, because it's like such a new area that where there is some research, but there is so much more that can be done, especially like on the upper end of video game expertise. So yeah, so some ideas that we had were to run some cognitive test batteries with professional players, and then compare that to just the casual players. You know, do we see any difference? Like, you know, start at the descriptive level and just look at it. What is there? Is there anything that could be of interest? Yeah, but we haven't done so yet, sadly.
That recruiting would be interesting and hard and long and definitely worthwhile. So Julian Abik is interested in asking his own question. So I'm going to click allow to talk. Go ahead, Julian. He's muted, so I asked him to unmute. I'm not sure. I'll wait while he perhaps gets, or she, I'm not sure, gets that together. I'll ask Mark McDaniel's question, someone who is also a One World contributor. He writes, very much enjoyed your talk. Could it be that training could be directed at adopting cognitive strategic orientations to a task rather than a cognitive skill per se? And this might show more transfer, building on your finding that participants reported adopting particular strategies for the training task.
Yes, I think that could well be, yes. I think, and that is probably where transfer could be very broad, right? Because then you kind of get like more of a, you extract something that is more general from it, that you can then use in many more contexts. And I was actually thinking about that when I saw your talk last time. So yeah, definitely. I think that is maybe something where additional metacognitive instruction could be useful, because I think often, like in the typical cognitive training intervention, we, in most of them at least, we don't tell participants what to do with whatever they improve, right? We just have them repetitively practice and do pre and post tests. But maybe for these more general skills, it could be useful to tell them, okay, this could be something that you have picked up. Do you think you have picked this up? How do you think you could maybe use that in a different context and so on? So I know that they did, or that there are studies that try to do that with specific strategies. So for example, instruct, I don't know, chunking strategies or imagery strategies or so. And that sometimes works and sometimes doesn't work all that well, but maybe that is too specific again, because that is very specific to the particular paradigm where the strategy works or the specific stimuli. But these more kind of general strategic orientations, for example, or something like just kind of getting that you can, that you should try to make the task easier for you, and that you could maybe use that in other contexts or for other learning contexts as well. That could be a useful thing to do. Yeah, but I think that it is a bit hard maybe to very precisely measure this and kind of, you know, operationalize what exactly it is and how to, yeah, so there's probably a lot of work that needs to go in first into understanding the task properly and what are these different strategic orientations you can have to that particular context of intervention.
Yeah. Priya Kalra asked a similar question about chunking strategies and other strategy use and whether it's trainable. So it seems like you've doubled on your answers there. So yay. Hopefully, Priya, that addresses what you were asking. Oh, Julian says he did not mean to click raise hand. He just meant to look at the Q&A.
No worries.
Got it. No worries. Okay. Just a couple of more questions if anyone else doesn't have anything that they'd like to kind of verbalize themselves. Okay. So Tom asked, better item memory without context implies stimulus-specific expertise, which is an interesting idea. So to apply the Carnegie Mellon approach, training leaves the trainees as novices, but with better novice knowledge. that is nothing deeper, but their service processing in the training task improves. And I'm not really very familiar with the Carnegie Mellon approach. So
yeah, me neither, unfortunately. I probably should be. I guess it depends on what you mean by surface, right? Surface processing. I guess it's a matter of definition a little bit. No?
Yeah, so Tom raised his hand, so I'm just going to go ahead and allow talk.
So the approach to expertise that a lot of people at Carnegie Mellon have taken in their developmental studies and studies of naive physics and so forth is that when you don't know much, you focus on the surface structure of problems, and you relate problems to one another based on whether they're about the same stuff or the same stimuli, and the solutions you come up with are based on extrapolations from the stimuli that are in it and so forth, not from the underlying physical principles.
Yeah.
Once you get to be an expert, you look at problems that are really different from one another and what they talk about, but they rely on the same principle. So that was kind of what I was getting at.
Oh, super interesting. Yeah, that is something that we actually want to do with the video gamers as well, where it's like they have like this much longer duration or kind of development of expertise than you have within just a single training intervention. And I think it's really interesting because, for example, for CounterStrike, when you first started, people who are novices in the game, they would often say, oh, this is just about clicking really fast and, aim and click. But this is not really like, once you can aim, well, everyone can aim after a certain time. And then it becomes much more about many different layers of performance in this task or in this context. And so something that we want to do, are very keen to do with our professional collaborators is to try to design situations that can differentiate between this more surface knowledge and surface focus on the surface of the video game versus kind of those aspects that can reflect true insights into the game. So, for example, integrating the information, making use of those different cues and so on in an efficient way, having that, what they often call game sense, kind of trying to understand what that is a little bit better. And then once we have that, then we can use those tasks to measure expertise in a different way. And then we can maybe also see better what happens when we train people in this or in similar kind of things, if that makes sense.
Question. So we have another question, again, more kind of on the applicability side. Expectation management can be quite difficult to control across treatment and active control groups. If you can control for motivation to perform across each cognitive task at the pre and post test, would you still be concerned with an influence from expectation bias? And again, perhaps that's, again, one of those distinctions between the video games and the lab-based experiments that you touched on.
You control for motivation to perform across each cognitive. Okay. No, I think, difficult to say. I would say if you had like a way how you could be really sure that without having an active control, you could still make sure that they have exactly the same level of motivation, but that's really hard to tell, because I think expectation is not necessarily motivation as you would measure it with the intrinsic motivation inventory or something. It's more kind of, I think it can be more subtle than that. So like when participants come in again and so we had that in like one study where our control group did a quiz, for example, as control intervention. And that is why we stopped doing this afterwards, because we had older adults, and older adults are better at quizzes than younger adults. And they got a real confidence boost. So I think it's more about self-efficacy maybe than motivation, actually. And they improved so much at post-test. So we saw like that the active control group improved even more than the working memory training group in some of our transfer tasks, which does theoretically just not make sense. So being good at a quiz should not make you better at a working memory task, for example. And so I think I think that expectation, confidence, self-efficacy, and so on, all these kind of things come together when it comes to these possible effects that can happen from pre-posters in taking part in such an intervention. It's often boiled down to, oh yeah, it's placebo or expectancy, but it's like much bigger than that. So I'm wondering how you could possibly really manage that and control that without an alternative intervention. I think I can't see a way at the moment.
It's a tough question.
Yeah,
Our last question in the Q&A. In music training, there's a 10,000 hour rule for professional musicians, but then there's a split. Some musicians continue improving, but others do not, no matter how much additional training. I wonder if this is what's happening with the aspiring video players.
Super interesting question. And I bet that is something that our collaborators would be very keen to know as well. Yeah, could be. I mean, I think we can all, like anyone who has a hobby that they did for a long time that they love, but just realize, okay, there's like a limit for me. I will never become better at, I know, dancing, singing, play CounterStrike. I can play as much as I want. I'm not getting better. So I could imagine that. I don't know. It's definitely something that would be interesting to follow up on these aspiring video game players, for example, to kind of, so what would be interesting as well, in addition to like some longitudinal studies or so that follow their path of learning, what could be also interesting is just to kind of follow up the same players like a year later or so and see in what kind of group would they now fall into. Did they make it to the semi-professional group, for example, or did they kind of take a turn over to the experienced group? And what makes the difference? Kind of, is it related to anything they did differently during playing, or is it, you know, just kind of this ability that they had from the get-go and that always determined where they would end up? So that would be very interesting to learn. Super cool question. Thank you.
Yeah. Lots of horizons, lots of different places that your work is likely going to go. So as just kind of a closing thought, do you mind just kind of giving us a little summative thing, and then we'll wrap up? Any closing thoughts that you want to share?
Okay. Yeah. so yeah, thank you very much. So those questions were super interesting. I really enjoy kind of hearing from people what they think. And I think what I found really interesting from the past couple of years working in this was really this shift also that you see in the research community, from kind of going from this, yes, it works, no, it doesn't work in cognitive training, for example, more towards like, okay, let's calm down. Let's look into what are the actual mechanisms, why it might work or why it might not work. And I think this is where it gets really interesting. It gets like into this nitty gritty, into the detailed level that is very complicated sometimes to really figure out and identify. But I think that is where it gets really interesting, despite the challenges. And I think it's like also like a really nice and fruitful avenue for trying to find ways where we don't have to ask so much about, does it now work or does it not work, but kind of can look more into, okay, are there maybe just some aspects that we could use, you know, and for creating or developing some interventions that are actually reliable and robust, where we don't have to fight over because it's just clear, and that where we can actually support people in their cognitive performance. Because I think as effortful as these studies are to do, but I think it's such an important question, so that we shouldn't stop asking it just because it makes work and is challenging.
Yeah, really bringing psychology to everybody. So thank you so much, Claudia. I really appreciate it. We all really appreciate it. And thank you to everyone in the audience. We encourage you guys, even though this is the last talk of our cycle for this academic year, we will definitely have more talks forthcoming. So just keep an eye on the website, and application information for a second round may be forthcoming in emails and other types of communications. But thank you very much, Claudia, again, and thank you all to the One World attendees.
Thank you.
Goodbye.